Morning or good afternoon, kids. Today we're going to be doing something asynchronously with fourth period. So here's the thing about this. We're going to be looking at certain triangles and we're going to be calling these special right triangles. And so the triangles are categorized as two types, 45, 45, 90 and 30, 60, 90. So first off, we're going to take a look at this right here. This is a drawing of a what we call a square. And of course, as we know, all four angles are 90 degrees. And this diagonal bisects this, cuts this square in two equal parts. And as you know, with squares, we have certain properties. All of the sides are all congruent. They're all equal to each other. And so we have 90-degree angles. This diagonal bisects, number one, the angle right here. So instead of this just being 90, you're going to go ahead and cut that 90-degree angle into two equal parts, which is 45. So this would be 45 degrees, and this is also 45 degrees. So this creates what we call a 45, 45, 90. Now we're going to go with the smallest side of the smallest square that we can, where all sides are equal to 1. Well, we can go smaller, but for all intents and purposes, this is going to be our parent 45, 45, 90 triangle. So right here, this being the parent, then that means that we're going to be looking at this particular thing. And basically, we're going to be looking at the measurement of that diagonal. So we don't have that here, but we do have that this triangle has sides of 1 and 1. So we're going to use the Pythagorean theorem to find out what this diagonal is equal to. So let's see, since we have legs and legs, this is going to be leg squared, which is 1 squared, plus the other leg squared, which is equal to our diagonal squared. Now we're going to solve for the diagonal. So 1 squared is going to be 1 plus 1 squared, which is also 1, equal to d squared. This gives us 2 equal to d squared. Then we just take the square root of that. Okay, so we have these measurements. So this is the smallest measurement for a 45, 45, 90 triangle. And so whenever we think about 45, 45, 90s, let me go ahead and put in this right here. This is actually a 45, 45, 90 triangle. It's being drawn automatically by the computer. We're always going to be dealing with these measurements, 1, 1, and square root 2. Now remember our rules on similarity. We had SSS similarity, SAS similarity, and we also have angle similarity. So as long as we have two angles that are equal from one triangle to another, as long as we have two pairs that are equal to each other, we have similar triangles. So any 45, 45, 90 triangle is going to be similar to any other 45, 45, 90. So when you think 45, 45, 90, you're going to have to go ahead and do this by measures of 1, 1, square root 2. So remember these ratios, and that's going to be the ratios of the sides, okay? Now we're also going to take a look at 30, 60, 90s, and that involves what we call an equilateral triangle. Let me go ahead and grab that and move it to the side, make it a little bit better. All right, so this line right here is what we call an altitude, which creates a 90-degree angle. Now this is a special type of altitude. Since this side and this side are both equal to each other, and let's go with the smallest sides, and this side right here from here to here is also 1. Since these two sides right here are equal, that means that these two are going to be equal. And as we know, with any equilateral triangle, all the angles are equal to 60. Now, when we bring this altitude down, we have certain measurements that happen. Number one, this altitude is considered what we call an angle and also perpendicular bisector. That means that the distance of the side that it intersects with is being bisected at this point of intersection. So let me see. So whatever happens right here, this distance from here to here, and let's go ahead and change the measurements because this actually works a little bit better, is actually halved. So I'm going to call this distance 2, this one distance 2, and this is 2. And 1/2 of 2 is going to be 1. So you can automatically assume that with any triangle like this. Also, this angle, which is originally 6 degrees, is bisected also by this altitude, which is now going to be 30 degrees. Now, we need to find out what the height is, or this distance right here. So I'm going to use Pythagorean theorem. We have a distance of 1. Because this is a right triangle, we can use the Pythagorean theorem. So it's going to be 1 squared plus, since it's legs, that's going to be h squared, and the hypotenuse is 2. So it's going to be 2 squared. So 1 squared is 1. Of course, that's going to be h squared equal to 4. Subtract 1 from both sides. So this is h squared equal to 3. Then we take the square root. So h is going to be the square root of 3. So that means that this distance, or the height of this equilateral triangle, is going to be square root 3. Now let me go ahead and clean this up. I'm going to go ahead and put in another triangle. It's not going to look as nice as that one, but you know what? You need to be able to go ahead and draw this in different orientations. There it is. So this is the triangle. Let me go ahead and do a couple of manipulations here. Number one, let's go ahead and turn it. Okay, and then we want to go ahead and flip this left to right. Oops, because it was originally somewhere else. So it's going to be flipped up and down. Okay, so this is the half of the equilateral triangle. If we take a look at the triangle right here, we're going to be doing this for this right side right here. And we're going to write the measurements. So we have distance of 2 here. Let me go ahead and get this to work. So we have a distance of 2. This is a right triangle. This is a distance of 1. And this one's square root 3. And remember, this is 60 degrees right here. Then we also have 30 degrees for this angle. And of course 90. So this is what we call a 30, 60, 90 degree triangle. Always between the 90 degree and the 60 degree angle is going to be your 1, or the smallest side. And it's opposite of the 30 degree angle. If we take a look at that, we can go ahead and take a look at that right here. The square root 3, which is now the middle side, because square root 3 is slightly larger than 1. That's going to be between the 90 degree angle and the 30 degree angle, but also it's opposite of the 60 degree angle. That's why we put it right here, square root 3. And the largest side, which is opposite of the 90 degree angle, is going to be 2. So it's 1, square root 3, and then 2. Okay, so just remember that when we're drawing these triangles, you have to draw them in a couple of basic positions. First off, there's this position, which is going to be for the 30, 60, 90 triangle. So remember, the smallest side is always going to have the 90 and the 60 degree angle between them. So that's going to be 1. This is 2, and then square root 3, and of course the 30 degree angle is going to be right there. Another way you can draw this is upside down. And the reason why we're drawing it like this is because you're going to find triangles drawn in these positions, and you might have to reposition everything or just go with the flow. I go with the flow, but whatever it is, whatever is given to me right there, I'm going to be using. So this would be our 1. Our other leg is square root 3, and this would be 2. And I think those are some of the basic positions that we're going to be drawing these triangles. So there's the left side of the equilateral triangle. Of course, you have 60 and then 30 right here. And between the 60 and the 90 is always going to be your shortest side. The leg that connects to the 1 is going to be square root 3. And of course, the hypotenuse, or the one that's in between 30 and 60, is going to be our 2. So however you want to think about it, you can draw them in those different positions. Okay, so let's go ahead and move on to the actual notes. So right here we have a triangle inside of the 45 degree angle. So of course they use these X's, but we're not going to. We're going to go ahead and figure these out a little bit differently. So find the lengths of the missing sides. So we could do this by the Pythagorean theorem. That leads into radical simplification, of course. Since this is 45, this has to be 45. And as you know, that this side has to be the same. And you can use Pythagorean theorem. But we're going to go ahead and use the stuff that we know about the new triangles. So remember, we have our smallest triangle that we can go ahead and use, which is going to be that small 45 degree triangle. Let me go ahead and copy this down another page so that way we can go ahead and get something a little bit easier to work with. So, as you know, one side was 5. Then we had our other triangle. Now we're just trying to find the missing sides. I don't even know what the triangle is named, so let me go ahead and get the name. A, B, C. Well, pretty simple. So this would be A, B was at the 90-degree angle, and C was where we are at. So remember that a 45, 45, 90 triangle had ratios of 1 to 1 to square root 2. And that's what we're doing with this, just using that ratio. So this would be 1, 1, square root 2. Then you ask yourself, all right, what do we multiply this side by to get this side? So then we just work with that ratio, okay? So we're going to take 1, multiply it by a number, and it's equal to that other side. Then we just divide both sides by 1. There's a reason why I'm doing that, even though it's not going to do anything for me, but that's going to tell me the scale factor. So now I'm going to multiply all these sides by the same scale factor. So I'm going to multiply by A. So this would be, let me see, for AB, that's going to be 1 times 5, which gives me 5. And for the other side, that's going to be 5 times the square root of 2. And that's my answers. So AC was, well, got that. So AC was 5 square root 2, and AB was just simply 5. I know it's a simplified way of thinking about it, but that works for us. Excuse me. All right, so here we have another triangle. It's still 45, 45, 90, but instead it's drawn like this. The hypotenuse is 4. So we're going to still use our smaller triangle with the measurements that we know. Now this being 45-degree angle right here, and this is 45. Between the 45 and the 90-degree, we're always going to have 1. Same thing over here. And then the hypotenuse is square root 2. And so then we're going to take a look at these two sides and say, well, okay, well, what do we multiply the square root of 2 by in order to get 4? So now we just divide both sides by square root of 2. I know I told you to rationalize the denominator, but I'll take answers like this. So this is your scale factor, because these two cancel out, and we have A is equal to 4 divided by the square root of 2. So now we say, all right, so I'm multiplying all these sides. So right here, basically, this is what we're doing. We're multiplying everything by A. So we're taking A times the square root of 2, we're taking A times 1, and also A times 1. So we don't need to do this one because we already have it, but we're going to be getting these two sides. So we have 4 divided by the square root of 2 times 1, and this is going to be 4 times the square divided by the square root of 2 times 1. And they're going to give us, lo and behold, the same thing, 4 divided by the square root of 2, and 4 divided by the square root of 2. Now, if you use the radical simplification, remember, you're multiplying by 1, so you're multiplying the top and the bottom by square root of 2. So this gives you 4 square root of 2 divided by, well, let me see, square root of 2 times square root of 2 is going to give you square root of 4, which is 2. And if you simplify that further, it's 2 square root of 2. So you can also do that, but that's for a little bit more advanced level. So this then is right here. BC is going to be 4 divided by the square root of 2, and same thing, 4 divided by the square root of 2. And I'm about to run down of time, but you know what? I can restart this recorder and just do another one. And you know, it just gets a little bit simpler. So we'll talk about this. Just give me 1 second.